Okie dokie smoky. Chapter 20. We're going to talk about the space between the stars, which is called the interstellar medium, and all the things that go in between it. So we got a stellar nursery here in this opening image, some baby stars forming there. We've got some gas, nebula here. We're going to talk about all this stuff. Okay, so the ISM, the interstellar medium. Interstellar, between the stars. Space between the stars, the gas that's between the stars, stuff called cosmic dust, particles from space called cosmic rays, and the life cycle of the stuff that makes the stars, and then our sort of local area called the local fluff. And it's the gas and dust that our sun and solar system are a part of. Okay, so the main question here that we're trying to answer is where did our solar system come from? How did the sun form? Of what material did the sun form? And that kind of stuff. So that's what we're going to really talk about because the space between the stars is filled with the proto-elements that make up the stars. And so this raw material is what we're trying to understand. Okay, so it's called the ISM. The interstellar medium is the space between the stars. There are some areas where the density of the gas is very high and it looks like a cloud, and so we call it a nebula. So that would be a space between the stars where the interstellar medium, or the ISM, is concentrated into a giant cloud called a nebula. Okay, and then there is most of the stuff is in the form of a gas, which means it's just individual atoms or molecules. It's not in the form of a solid, like a granite countertop or something. But 1% of the ISM is actually made of grains or larger things like bits of rock or ice, and that's called interstellar dust. So slightly different between the two things. Most of it's gas, some of it's dust. Just 1% is dust. Okay, so here's a cool picture. We've got some little baby stars here forming. There's a little cluster there, but you can see all this gas in between. There you go, this dark cloud of gas. Okay, and these bright clouds here and all this stuff. So what we're trying to understand is, obviously these stars are forming among this gas, so what is this gas made out of? So there's the various types, the dust and the gas, and the gas can be made of different materials, mostly hydrogen, but some other things here. Okay, so the interstellar gas is mostly hydrogen, ionized hydrogen. That means it's got some energy in it, so it glows a certain way. And the strongest line, when we've talked about absorption lines and emission lines, the strongest or the brightest line that's easiest to see is the red line. And that line is typically called the hydrogen alpha line, and it's 656 nanometers, I believe. Okay, so H alpha. So the H alpha, 656 nanometers, that is a specific transition of the hydrogen atom, and you can see most of the filters on the sun use the H alpha filter, and so the sun usually looks red, but that's the specific transition. If you imagine these rings are the energy levels of an electron. When the electron transitions from the 3 to 2 state, so 1, 2, 3 lines out from the center of this ring. Let me just draw a little picture here. So 1, 2, and 3. So when it transitions from the 3 level here down to the 2 level, every time an electron makes that transition, it emits the 656.3 nanometer photon. Okay, so that's the H alpha line, and that's the brightest line in space. Okay, so this is the Orion Nebula, and a nice picture of it, seeing all the different colors. The red glow, that's in this nebula is that hydrogen line, and blah, blah, blah. Continuing on here. Blah, blah, blah. Okay, so in order to get the ionized hydrogen, so it's a little bit, so this is what we call H2, then you need to heat up the hydrogen before you get that. So the neutral hydrogen clouds are where the gas between the stars is a little bit cooler. So only a small fraction of the interstellar medium is close enough to stars to be ionized. So that means most of the hydrogen is in this neutral form. But, as this says, neutral hydrogen atoms at temperatures in interstellar space, which is the space between the stars, is not hot enough to react basically with light. So it's hard to see that. But by looking at the absorption spectra, we might be able to see some evidence of this stuff. So, yeah. So this is talking about how if you have the gas in between a bright object or something, you might be able to see the absorption lines being stolen by the gas that's in between the stars. So this is a diagram of that. You've got the star over here, okay, and it's emitting light, and as it travels through the gas and dust, you can see how initially you have 1, 2, 3 absorption lines. After this light from the star makes it through this interstellar dust, suddenly you get a few more absorption lines being missing. And so then you say, oh, okay, this star must have traveled through some gas, and the gas absorbed some more light from it, and then remember that those lines correspond to the elements that make up the gas. So that is one way for us to determine what a gas is made out of. A cold gas is by looking at light that's gone through it from a distant star. Okay, so, and anyway, now we're talking about the 21 centimeter line. So this is another wavelength of light that comes from hydrogen. And so, for example, it says an excited atom can lose the excess energy by colliding with another particle or by giving off a radio wavelength of 21 centimeters. Okay, and so if you excite some hydrogen, it will wait an average of 10 million years before emitting a photon. That's on average. But there's so many hydrogen atoms out there that you get enough to generate this line of 21 centimeters. Okay, so yeah, there's some telescopes here. These guys made a telescope to measure that radiation. Okay, and then there's areas of space where it's even higher than the space around a star. So let's say you have 2 stars, 1 star, 2 star. You've got some gas and dust near the star. That's going to glow some color. You might have the same gas here, but it's not going to be as hot because it's far from the sun. So then when the sun's light goes through it, it's going to absorb some of the light. And then there's going to be some areas where so this is what, 10,000 degrees, or 10,000 Kelvin, and this is, much colder than that, a few Kelvin. And then you've got areas where it could be 1,000,000 degrees or 1,000,000 Kelvin. So where that happens, the energy is high enough to ionize the oxygen atoms, for example, 5 times, and that means you strip 5 of the electrons out of the outer layers of a oxygen atom. So let's say you've got an oxygen atom here, and you've got a bunch of electrons in it, and I'm just going to draw the 1, 2, 3, 4, 5 of them, and you just knock them right out, so that oxygen atom doesn't have as many electrons as it should. So in order for that to happen, you need very high temperatures. So where that occurs is usually around a supernova, and that's when a star explodes and just puts so much energy out into space, it can heat up gas to millions or tens of millions of degrees Celsius, or at that point it's similar to Fahrenheit and Kelvin, they're all the same, millions of degrees, okay, or millions of Kelvin. In our galaxy, there's about 100 billion stars, and only 1 every 100 years on average happens in our own galaxy. So supernova are pretty rare in our own galaxy, but they happen pretty frequently that we can see across the universe. So we're able to take pictures of them and study them as they occur on a somewhat regular basis, at least more than once every 100 years across the universe. But when these supernovas explode, they emit a ton of energy. Okay, so we've got our three types of interstellar gas. If you've got a star, you've got gas near a star, you've got gas away from a star, and you've got gas near a star that has blown to smithereens. And that all three gases, even if they are made of the same material, they're going to emit different types of light and appear differently. And so that's how we can study what the ISM is made out of, by using all these different techniques. Okay, so there's an important thing we've been talking about, how atoms leave their fingerprints, their spectral fingerprints, using absorption and emission lines. But also you can study what molecules are made out of by looking at radio and infrared waves. So we've been able to determine if there's carbon or oxygen or hydrogen out in space, but now we can discover and observe whether or not there are actual molecules like H2O or other things out there in space by looking at the light. And those are called molecular clouds. And molecular clouds have a little bit more complex elements to them, and they have more higher densities, so they're not as empty or vapid. They are quite dense and filled with lots of good things. So some of the things that we see out there: H2O, water, carbon monoxide, ammonia. We see that stuff out in space. H2, remember H2 is heavy hydrogen, deuterium. There's acetic acid. There's sugars. There's some more complicated things out there. All kinds of different stuff: formaldehyde, acetylene, acetic acid, ethyl alcohol, ethylene glycol, benzene, formaldehyde, ammonia. Okay, all these things are out there in space that we've been able to detect. Cyanoacetylene, acetaldehyde, this stuff here. Very important for amino acid formation. So, where did the complex building blocks of life come from? Well, we're starting to see that they're pretty regular out there in space, and so they could help seed life or create the initial ingredients, at least, for the possibility of life to develop. Whether or not life will develop necessarily with these ingredients, it's hard to say. So we really don't know if life is super easy to make or super hard. We could either be one of many civilizations or the only one. We're still trying to figure out what leads to the odds and makes it possible for intelligent life to develop. Okay, so cosmic dust is different from gas. So we've been talking about the gases. You've got hydrogen, heavy hydrogen, you've got other things out there, and then molecules made out of those fundamental things. But now there's things called cosmic dust. So this is a picture that is oftentimes shared on social media to represent a spot of the galaxy where there's, or a spot of the universe where we don't see much. We call it a void, an area where there's nothing. Well, this is just a black cloud, and it's absorbing the light from the stars, so you can't see through it. This is not a void in the universe where there's nothing behind it. This is a cloud of gas, and it's just an interstellar cloud. And it's relatively close to Earth. There's no stars between us and it, so it obscures the light from the stars behind it. Okay, and so there's nothing crazy about it. In fact, if you look through that same thing, but in infrared, there it is again, and now you can see the light traveling through it. So Barnard 68, we can see if we use an infrared filter on our camera, our telescope, and just look at the interstellar light through infrared, the infrared light will pass through the gas and dust, allowing us to see the stars on the other side. Okay, so if we look here, remember the full spectrum of light is from gamma rays. So you got gamma rays, you've got X-rays, you've got UV, you've got visible, you've got IR, infrared, all the way to Wi-Fi, to microwaves, to radio waves, and so on. That's the full spectrum of light that's available to us. And our telescopes try to look at all those different things because you're emitting infrared light, whether your eyes can see it or not. You're emitting visible light, you're emitting all kinds of different energies that telescopes can see with special filters. So this is a famous nebula. This is the Horsehead Nebula. It looks a little bit like, maybe a real horse or a seahorse. But that's the Horsehead Nebula. And there it is again in a different wavelength of light. And suddenly the horsehead feature that we normally associate with it doesn't look so striking now because this is just the way it looks in one wavelength of light. Okay, so in part A, this is visible light. That's what we would see with our eyes if we could see it. We can't see it because it's too dim, so we need these telescopes and cameras to see it. But here it is in infrared. It's almost gone because the light doesn't get darkened by the clouds in infrared. So it allows us to see through the clouds. This is the galaxy in infrared. So it's very bright here. Normally when you look at the Milky Way galaxy, in the plane of the galaxy, it's very dark along here because of all the dust. But with infrared light, you can actually see it. And so astronomers are spending a lot of time using infrared and longer wavelength radio waves to penetrate the dust and gas in the galaxy to see through and understand what our galaxy is doing. It's very difficult to study our own galaxy from inside of it because all of the material gets in the way of seeing across it. So it's hard for us to determine that stuff. Very tricky. Okay, this is the Pleiades. This, if you look closely at the Subaru, if you own one, the Subaru car company, the logo is the Seven Sisters, which is the Pleiades, and Subaru is the word for the Pleiades in Japanese. So there's a lot of references in business and life and pop culture using astronomy as the guiding point, including Sirius XM satellite radio. You've got Subaru and other things like that. Okay, so all this knowledge that you're gaining from this course is helping you appreciate, the world around you a little bit more. Okay, interstellar reddening is another thing you got to understand, and or interstellar extinction. So basically, if you've got a cloud of gas and dust, you might have your rainbow of light coming in, and as it goes deeper and deeper and deeper and deeper, it just fizzles out. And so if you are here, you might be able to see the light. If you're here, it's getting dimmer. If you're all the way over here, you won't see any light at all. So basically, the distance you travel through gas, the less further the light gets. So the light gets attenuated, it gets dimmer and dimmer and dimmer and dimmer and dimmer until it doesn't make it through. So when you're looking through gas and dust, you can't see the light. And that's a perfect example of this. When we looked at through the gas and dust here, there's so much gas here that the light doesn't make it through. And so what ends up happening by looking at this, you see infrared light makes it through. Okay, so that means we have our Roy G. Biv, our rainbow, and all of this light, the blue, indigo, violet, the green, the yellow, all that dies. The only light that makes it through is the red and the orange, and that's what this is showing you, is that red and orange light makes it through. So only red light makes it through. So this is why it's called interstellar reddening, because the light that actually makes it through is only the red light that survives. So basically it's like a red filter or a red gel on a theater light to make everything appear red. It's only letting the red light through. It's absorbing all the other light. And so that's what interstellar reddening is. And this is another example of that. Your star is emitting all light. It hits the dust, and just like a sunset, it will scatter blue light perpendicular and transmit that red light right to you. And so, that's why the sky is blue. You got the blue light being scattered or the red light being scattered at different angles, and so you end up with only red light making it through. Okay, interstellar grains now are a little bit larger things than gas and dust. Or they're kind of like dust too, some of the dust particles. So some of these things, there's a bunch of this floating around. You've got some water ice, methane, ammonia floating around out there. There's, theorized that the water on Earth could come from a lot of these little bits as the clouds collapse and form into planets and stars. And enough of these things get together, you could have H2O build up enough to fill the oceans of Earth with water, or they could come from comets that hit the Earth and deposit the water the same way. Okay, so anyway, this is just another thing to be aware of out there in space. So remember, we got 99% gas out there, 1% dust, and some of that dust is are these little grains that are that could be responsible for depositing the water in the on the Earth. So they have these little rocky cores in the center. They've got soot, little dust particles, just like in your house. Okay, they're very small, right? Smaller than the wavelength of visible light, and so on. Okay, so then finally, there is a thing called cosmic rays. So cosmic rays are particles that come from space. Okay, it's not a ray of light. It's not a ray of whatever. It's a particle. And this guy started realizing they were there with his hot air balloon. He took them up, a hot air balloon up into space, and he could measure that higher up you have more cosmic rays. And that means the atmosphere is stopping some of them before they hit the ground. But it turns out that they come from sources that we're not completely aware of. Some of them come from the sun, some come from black holes across the universe, some come from supernova, some come from all sorts of other things, magnetic fields in the galaxy, accelerating the particles around, but all kinds of stuff. And there's that word positron again. Remember, that's antimatter, that's the anti-electron. They are close to 90% the speed of light. They're just pretty cool. So where do they come from? Hard to tell. Some of them come from, like I said, within the galaxy. They could come from outside the galaxy. They could come from the sun. They can come from Jupiter. They can come from all kinds of different places. But anyway, some of these, travel for really long distances before they reach us. The highest energy cosmic rays probably come from supernova explosions. And some of those particles are ejected out and go across the universe and smack into us. Could be from black holes that are accelerating particles from really far away, for some of the highest energy ones. Again, we're still figuring out exactly where that stuff comes from. Okay, so now we'll talk about the general flow of this material as it moves from the galaxy. So here's our galaxy. Every time a star goes supernova, some of that material gets ejected out into space. Okay, there's interstellar dust that's constantly being accreted onto the galactic plane. Gravity's pulling dust in from the voids between galaxies, so we're adding mass in. So there's this cycle of energy, or a cycle of matter, where mass falls in, turns into stars, stars burn, blow up, scatter stuff back out into space. And so there's this sort of flow of energy. Okay, and so at any given time in the Milky Way, the majority of the ISM, or the gas in the interstellar medium, is in the form of hydrogen. So hydrogen is most of the stuff in the universe. The molecular clouds are roughly 30% of the total mass of the gas between the stars. The amount of hot gas produced by supernova is small, just because there's not so much of those going on compared to the other stuff. But here's the idea, is the ISM is not a closed system, so gas is constantly falling in from outer space between the galaxies, and then you're constantly forming new stars and going supernova. And the process of this cycling of material is called the baryon cycle. And that's just the particles coming in, being turned into stars, and then re-emitting out as supernova and other end states of stars. Okay, so that's the main stuff for the cycle there. There's a little bit more here that you can read about. But then finally, the ISM around the sun is called the local fluff. So the local fluff is just the area around the sun immediately. So here's the sun. The sun is flowing this way through this cloud of stuff. There's Sirius, one of the closer stars. Alpha Centauri is here. So remember, Alpha Centauri is about 4 light years away. Sirius is about 10 light years away. And so those are some stars in our local area. And you can see there's just this huge cloud of gas and dust around us that we're in, okay? And so this is called the local fluff. And then this direction would be towards the center of our galaxy. Okay, so in summary, you've got the ISM. And the ISM is the space, is the stuff that's between the stars. It's what the space between the stars is made out of. About 99% of it is gas, about 1% is dust or grains. The gas has cold hydrogen, ionized hydrogen, and super duper hot hydrogen, millions of degrees around some stars. Cosmic dust, there's dust can be seen when stars are behind it, when it scatters light off the side of it, you can see it from the side, or because of interstellar reddening. And there's reddening and interstellar extinction there. And cosmic rays are particles that come from space that are very high energy. They could be a proton or a proton and a neutron. And then also you could have electrons or positrons coming from mostly supernovas, shooting particles out everywhere. And then the galaxy eats material from outside of the galaxy. It turns it into stars. It re-emits it in the form of supernovas and other things. And then finally, the ISM around the sun is called the local fluff, and it's a local bubble of energy that's a region about 300 light years away from the sun, where the ISM is a little bit slow. Okay, low, so the density is low. Okay, I think that's all I have. I'll see you guys later.